muted. There we go. I was muted. Hi there, everyone. So today we're going to jump back into talking about algorithms. We're going to kind of pick up where we left off. Hello. I don't have any kitties downstairs today, so sorry in advance for that. Maybe one will swing by. Anyway, we're going to pick up where we left off last time. So last time, we were talking about measuring efficiency. And the idea is when we're analyzing an algorithm, we start by not looking at the exact runtime, because the exact runtime is going to be different from computer to computer to computer. Supercomputers are going to run something faster than your laptop. But what does not change from computer to computer is the rate of growth of the algorithm. That is, as the input gets larger, how much longer does it take? And I framed this in the context of doubling time. So we talked about the idea of if I double the input size, n being just kind of a variable for the number of elements in our input, which again depends function to function what exactly that means. It could be the size of an array, or it could be the value of an integer input, whatever. If I double size the input, how much longer does the algorithm take to run? And we talked about how if a function has linear growth, that is to say, if it grows linearly, an example of this, adding to the front of an array list. This was linear because we have to shift n elements over to make room for the new element. If I double n, 2n, I'll just say double n, double runtime, something like that. If I double the size of the input, it doubles the size of runtime. However, if this runtime is quadratic, and quadratic means proportional to n squared. This means if I double n, rather than doubling the runtime, it quadruples the runtime. And this is true for any computer. Now, you can talk about multi-threading and things like that, but in absence of multi-threading, if you have a quadratic rate of growth, what that means is if you double the input, rather than doubling the runtime, it actually quadruples the runtime. Even worse, and we'll get into more formal definitions of this later, if we say a function is exponential, what that means is it is some value, for now we'll say 2 to the power of n. In the case of 2 to the power of n, if I double n, it doesn't quadruple or even octuple the runtime, it actually squares the runtime. It raises the runtime to the power of 2 when I double the size of n. So the point is, exponential is really, really, really bad. And we'll get into how bad. If you remember, I linked a Minecraft video. If you had a chance to watch that, you kind of saw the exponential growth of the universal death clock. How you get to the 5th clock and you're already talking about, really long time frames that human beings won't survive to see. So any questions so far to get started? So again, when we're measuring the algorithm itself, we're measuring its nature. We're not running it on a computer to determine this. So growing fast is bad, and the reason growing fast is bad is, should we be familiar with log growth? We will be, and we'll talk about log growth. There's a very practical example that I can give for log growth. But if runtime is smaller than 1, exponential will be lesser. Well, so remember, we're not talking about runtime as a fraction of seconds. We are talking about a number of operations. So we never have less than one operation. Because remember, we're not actually, think of it as a number of clock cycles. Your computer can't do anything in less than one clock cycle. And yes, you have billions of clock cycles per second, but if I square the runtime it's not squaring half a second. It's squaring, in the case of my computer, that would be about 2 billion clock cycles. So now we're squaring 2 billion. That's going to give us 4 times 10 to the power of 18, which is much, much bigger. So don't think of it, these operations, as fractions of second. Think of them as whole clock cycles on the computer, because they're not fractional. So think of, when we're thinking of runtime, we're not thinking actually of seconds. Rather, we're thinking of clock cycles, and everything happens in whole numbers of clock cycles. There are no fractions of clock cycles in this context. And again, the reason we think of it this way is that the time is very relative to the hardware. If you double the speed of the processor, the problem will take half as long. But the growth will not change. That is to say, even though the processor is twice as fast, doubling the size of the input will still grow the problem. And the reality is, we want to solve our problems faster, which means we want less growth. So an algorithm that grows more slowly will be considered better in this context. So we talked about how to count operations. I did an example with the list analysis. Specifically, I talked about this, I did it actually with stacks and queues. I looked at the grow if necessary function for queue, and we looked at how long this would take. Now, something so people cannot actually link videos in chat, but if there's a video that you are looking for that's relevant, I can certainly try to track it down if it's related to class. Are you talking about the Minecraft video? I can just link it again, but that does not give you carte blanche to just ignore me for a bit and watch it. I'll go ahead and link it again. There it is. Anyway, sorry about that. So the idea here is, again, we're looking at it and we're counting the number of steps. So the number of steps is not actually a precise number, because here's the thing. This x plus equals 5 and this x times equals 5. We would count both of these at a high level as one step. But the thing is, this is faster on any hardware I'm aware of. And this is slower on any hardware. Multiplication is slower than addition at a hardware level. But we don't actually really care specifically about that when we're talking about analyzing our algorithm at a high level. We're just looking at steps broadly, and steps relative to the size of n. So again, when we looked at this function, this loop runs n times, n being the size of our queue, the queue array being elements. If I double the size of elements, this loop takes twice as long to run. This means that it grows linearly. That means as I increase the size of my queue, this step takes longer and longer, but that is a linear growth. What that means, linear, is that we can define the number of steps, t of n, that is, this is a function for the number of clock cycles, t of n as some constant c times n plus some other constant k, where c and k are greater than 0. And I know I'm throwing some math out here. Apologies in advance, there's going to be some math in this class. So what this means, though, is that this rate of growth is linear. Now, it doesn't mean it exactly doubles. We're not saying that this is an exact double. Rather, it roughly doubles. For example, if c were 3 and k were 5, let's say hypothetically this were the case, t of n, where n would be 10, so t of 10 would be 30 plus 5 would be 35. T of 20 would be, in this case, 60 plus 5. Now, that's not exactly double. Rather, it's a little bit less than double. But as n gets bigger, this gets closer and closer to double. That is to say that as n gets larger and larger, we get more consistently approaching. Doubling the size of the input doubles the runtime. Now again, we're talking about this at a high level of steps, where steps don't exactly translate to a set number of machine instructions or a set amount of time. We're talking vaguely. No, I don't know what you mean by the last part. If you have a specific question, I'd be happy to answer it. Sorry, this should be 5. T of n, this is number of steps relative to size of n, where n is the input. So if, say, a function took, an example of this would be a loop that has 3 statements in it. Actually, this effectively does 1, 2, 3 statements. And then I had 1, 2, 3, 4, 5, technically 6 lines of code, but let's just cut that one out so we're 5. This would be a way that we would calculate this. So we're not directly interested exactly in a runtime. That's not what we're trying to get to here. And I know I keep repeating that, but it's because I really want to nail that point home. Rather, we are interested in how quickly the problem grows with respect to n. An example of this, and we'll talk more about searching and sorting on Monday, but an example of this, I have a program here that performs any number of searches or any number of sorts that I want. And we'll actually work through this file on Monday, so I'm not really interested exactly in how the sorts work. What I'm going to tell you is that I'm going to do a sort called a selection sort. And this is a quadratic function, which is to say, it's a quadratic growth function. This means that double n quadruple the runtime. And again, I don't mean exactly clock cycles. We're being very fast and loose with what a step is. Because again, we don't really care exactly how many clock cycles something takes. We just want to know how much it grows. So this is going to be selection sort. And I set up a certain run configuration with these command line arguments. It runs a selection sort. What this is going to do is generate 10 million values. It's going to sort a list of 10 million random values between 0 and 200 0 and 20 million. And so when I run this program, you'll see this is going to take a while. Sorting 10 million values takes a long time. In fact, so long that we're going to check on this later because it's not going to finish anytime soon. So now, again, when we're counting operations, we're focusing on the algorithm's basic operations. Inevitably, we have some critical section. The critical section is the code that runs the most. So for example, in Q, this line of code is the critical section because it runs the most times. This means that if we were looking to optimize our code, any optimization we do in the critical section will have significantly larger impact on the code than anything outside the critical section, usually by multiple orders of magnitude. So the critical section is the section of code that runs the most. By the way, this code still not done. We'll keep an eye on that. So, when we're analyzing an algorithm, we're going to do this from the context of what we call asymptotic analysis. And asymptotic is a hard word to say. But what we are trying to do is we are trying to get an upper bound on how much more time this program will take as we increase the size of n. And so, asymptotic analysis is the estimate of, as a function input size, n, gets large, how much more time will it take? And again, we mean this very fast and loose, relatively, how many more operations will it take? So, an insertion sort, which is similar in runtime to a selection sort, the number of steps is proportional to n squared. What this means, again, if I double the size of my input, it will quadruple the runtime. Think of it in that context. So as n gets large, these differences become apparent. So we're going to talk a bit about merge sort later. The point is, this is better. N log base 2 of n is better than n squared. We'll see how much better later. But for now, just the point is we can evaluate these two algorithms as taking this many steps, and we focus on the n terms. So, we're focused on how much bigger, how much faster f of n grows as n gets large. How scalable is the algorithm? And generally, the slower the rate of growth, that is to say, the less the runtime grows as n increases, the better. So, we've already talked about linear time and quadratic time. Linear, remember, this means if n doubles, f of n doubles. Whereas quadratic, if n doubles, f of n quadruples. So in this case, because of this, linear algorithm will always be asymptotically better. Now you may be thinking, wait, but what if this constant were really, really big? Well, let's go over to the whiteboard. So hypothetically, let's say that I have two runtimes. I have one function that takes 100n. And I have another function that takes, and I'll call this g of n, that takes n, let's say n squared steps. Now, okay, sorry, I just saw a question there and I want to make sure I had already answered it. Now, if I say initially n equals 5, that means my f of n takes 500 steps, whereas my g of n only takes 25. And you're thinking, wow, this is a lot better. Now let's double n. N equals 10. When n equals 10, this number becomes 1,000. This number becomes 100. This is still significantly smaller. But I want to point out this ratio. This ratio, 500 divided by 25. This is equal to 20. That means that this approach is 20 times faster. But as n increases, now this ratio is 10. This is 10 times faster. If I double again, this becomes 2k, and this becomes 400. Now it's only 5 times faster. And if you were to graph these two functions, it would look something like this. And then the scale is a bit distorted here, intentionally so, just because I don't want to draw like 100n would be a near vertical line. So imagine that I'm stretching the y-axis considerably. This line would be f of n, and then let me find my blue markers. This blue line would be n squared. And at some point, these two lines would cross. And after this point, and this point is where n equals 100. At this point, these two values are equal, and then any time past this line, anything to the right of this line, no matter how much bigger we get, f of n will be faster than g of n. So even though we may think for small values of n that this algorithm is better, we're actually not even that interested in the fact. What we're interested in is as n gets bigger, which function is better. So in this case, even though g of n is better 0 to 100, we don't actually care. What we care about is which is better as n gets bigger and bigger and bigger. That okay, I'm not gonna lie, that gets a chuckle. I'll allow it. I'll allow it. Um, although I can program in C#, I should note that. So it's technically not accurate. Anyway, so the point here is we want to know how this grows. Is it helpful to find the intercept of the two algorithms? It's not that it's unhelpful. It's just that it's not particularly important. Can we essentially ignore the constants? Yes. So this is where it gets into an issue. Now, certainly, if say I had two functions, let's say I had f of n, which is 5n plus 10, and g of n, which is 6n. F of n is better, and I'm not going to pretend it's not better. But how much it's better is limited. It's not a significant amount better. Oh, I thought it was funny. It's not a significant amount better. We would actually say that both of these algorithms are linear. Maybe if I can spell the word linear correctly. Both of these algorithms are linear. So from a wide standpoint, stepping way back, we would actually say both these algorithms are in the same complexity order. That is, they're in the same complexity class. So it's not important which algorithm is faster with smaller inputs because the algorithms are really, really fast with smaller inputs. I don't want to say it never matters. There are cases where it matters, but for the sake of this class, where we're just taking a very foundational look at algorithms, we're not really interested in small values. We're only interested in very large values. I don't want to say it never matters, but it can matter, certainly. But so, for example, now we have these complexity classes. And I'm going to show these off. These complexity classes are as follows. F of n equals n. This is linear. F of n equals log base 2 of n. This is log. Does the same complexity class mean they have the same rate of growth? Yes. At a large scale, yes. Maybe not exactly point for point, but at a it means if you double the runtime, if you double the input, you can expect roughly double the runtime. Yes. In the case of linear, regardless what the constants are. So we're really not interested too much in the constants, even the coefficients, when we're talking about complexity class. So these are our complexity classes. We have linear, we have logarithmic. This is called log linear because it's n times the log, so linear times log, log linear. This is quadratic. This is cubic, or to say just it's to the third power. And this 2 to the n is exponential. And if you look at this, you may say, wow, cubic's really bad. It's growing so fast. It's growing even faster than exponential. Put a dog ear there. We'll come back to that. But as you can see, log is the fastest. N, which is linear, grows almost as slow as log from this perspective, but we'll talk about why linear is significantly better than log. And then log linear almost looks like linear, just with a steeper slope. It's kind of hard to see that yellow, admittedly. But now let's zoom out a bit. And when we zoom out, you'll see that it doesn't take long for the exponential to actually pass cubic. And in fact, it is true such that ultimately any exponential function will outgrow a polynomial function. All you need is a big enough n, and this will always be true. Exponential, therefore, is always worse. Is there O of n factorial? So O of n factorial is actually even worse than O of 2 to the n. That is exponential. O of n factorial is even worse. Naive traveling salesperson, and you may have seen that. If you're not familiar, you can look up traveling salesperson, is factorial. And factorial is really, 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 really bad. Hilariously bad. Unbelievably hilariously bad. By which I mean, if you try to solve a problem that has, say, an input of 100, and the algorithm was factorial. So input size 100, algorithm's factorial. You will need the rest of the lifespan of the universe, counting the end of the stellar period where new stars form. We're talking like black hole era and towards the end of the black hole era. That is how much time you'll need to solve that algorithm with size 100. Factorial is hilariously bad. What are the x and y axes? So the x-axis is n. It's the size of the input. The y-axis is the number of operations. Roughly equivalent to time, though not exactly. Sorry, I forgot to turn Discord off. Just 1 second. I'm going to mute it here. There we go. I know those pings are annoying, so fix that off. Roughly equivalent to time, but is constant runtime the best? Yes, so constant runtime is the best. So we actually haven't talked about constant time, but constant, what this means is that the size of n has no bearing on the runtime. An example of this is accessing an array at value n. The size of n does not affect how long this takes. Not in a substantially dramatic way anyways. So the size of n doesn't really matter. Why isn't log better than linear? Log is better than linear. So in order from best to worst, it is constant, then log, then linear, then log linear, then quadratic, then exponential, and then factorial, which is so far down here it doesn't even bear talking about. So remember that log, when we're talking about log, we're talking about base 2, generally in computer science. So let's go and let's try to give some so these are order classes. The idea is, for really large inputs, are these functions different? And the answer is they're both quadratic. That is to say, this function is better. It grows more slowly, but it still grows quadratically. And so when we're talking about the complexity classes, this is best to worst. Log is better than linear. There's a separate thing, log linear. So the complexity classes for this. No, I haven't said this. I don't know where this. If I at any point said that linear is better than log, I clearly misspoke. That was never an intention. Constant is better than log, but constant is not the same as linear. So constant, what this means, if n doubles, the runtime does not change. That is to say that the size of the input has no bearing. An example of this is getting the first element of an array list. If I get just not remove, but just get the first element of an array list, it doesn't matter how big my array list is. It will always take the same amount of time. If my array list is size 1 billion or my array list is size 3, it takes the same amount of time to get the first element. That means constant time. From here, we have, and I'm writing this using big O notation, log of n, and I'm just going to put a note here, base 2, generally. Although the base, it turns out, doesn't matter, because all logs grow proportionally. But this means log base 2. And we'll get to a practical example of that in a second. From there, we have O of n. This is linear. Log linear is O log of n times n, or generally you would see it written as n times log of n, which is worse than linear, but not dramatically so. Quadratic, this is O of n squared. Exponential, this is O of some constant to the power of n. A being a constant, we generally will say 2, but it doesn't have to be 2. It could be any constant. And then down here, factorial, which is hilariously bad, is O of n factorial. By the way, in case anyone was wondering, it's not done yet. Will linear ever intercept past log linear? No. So log, because remember, because we're dealing with positive numbers, log linear, this is the log of a number is going to be positive, and it's going to be greater than 1 in this case, because we're talking about numbers that are larger than base 2. So it's going to, so this is going to log, so we're talking about log n is still going to be greater than 1 in this case. So this number will be bigger than this as n grows. As n gets larger and larger, this number will be bigger, which means worse. So linear will never pass log linear. The difference actually gets bigger over time. As n gets larger, the differences between these classes get bigger and bigger. At small values, you may not see much difference, but at very large values, it will absolutely matter. A linear function is always better than a log linear function, but a log function is better than a linear function and a log linear function. So let's try to give some examples. So first, when we're looking at an algorithm, what we're actually interested in is the highest order term. So that is, what is the worst term with respect to complexity class? So for example, in 100n squared plus 50n plus 7, we only care about the n squared. This is the largest term with value n. We can pretty much ignore these. We can pretty much ignore that. Now, there's a mathematical proof I can show you. And what it would be saying that this is less than 100n squared plus 50n squared plus 7n squared for any n greater than 1. And that this would be equal to 157n squared. And this would be a more mathematical proof. But the short version is, if you see this function, mentally block out these two. We don't really care about the constant. This is O of n squared. That's the short version. It would, don't, in a more mathematically precise course like in algorithms, you would actually have to demonstrate this. Also keep in mind that if the function were this way, the largest term in this case is actually 50 to the power of n. I am streaming all my classes for now because we're not physically in the classroom, but thank you for the compliment. So again, we're talking about what the largest term is, and in this case, because this term is exponential, it's worse than the quadratic term, and so we would say that this is O of 50 to the n, something like that. All right, so now, let's actually take a step. We've already talked about the common. Let's look at some practical examples of this. First, As n increases, the margin of error of our estimate decreases more and more. Give me. All right, that's an as much as I appreciate the jokes, let's please not post them until after class. After class, we'll call it joke. It'll be joke day. We'll have a joke day after class. I'm totally fine with that. Just not during class, please. Bad jokes encouraged after class. I'll even change the title. The point is that our estimate will initially have a bad error. If we have a good big O approximation for small values of n, the error margin will still be high. But as n gets larger and larger, the results get more and more consistent. So this is why we're thinking of things in terms of large values. So now, let's look at some examples. First, let's talk about constant time. This means that the size of the data structure does not matter. So push and pop, generally, for a linked list, they're always constant time. For an array list, you have to worry about that growth if necessary, but it turns out to be something called amortized constant time, which we are not going to get into in this class, but you would certainly get into in, say, an algorithms class, or maybe even in 2150. I'm pretty sure you talk a little bit about it. Insert and remove from a queue, also constant time. Conditional statement for a loop. What this means is whether or not we enter the loop, not the loop itself, but whether or not we enter the loop. That is a constant time operation, typically. Creating a variable or assigning a variable. These are constant time. It doesn't matter if you're assigning x to 5 or 5 million. It takes the same amount of time to copy all of the bytes. Now let's give an example with logarithmic time. We're going to play a game. I'm thinking of a number, and I'm going to whisper it here to... and I can't, let me whisper it to I'm subbed. No, I can't whisper it to you. Okay, well, I'm just going to... I'm going to PM a TA a number. I can't actually do that either. That's right, because I disabled whispering in my class so people couldn't whisper me. Okay, I'm thinking of a number. And what I'm going to do is I'm going to write it on this notepad file. I'm going to write it down here. And I'm just going to slide this off the screen, but I'm going to write a number down. And I'm thinking of a number from 1 to 100. And I will tell you whether your guess is higher or lower. So, hang on. I will tell you if your guess... There's no prize. What instead I want to do is I want to work out a solution to find the fastest. I'm not actually going to tell you what the number is. Instead, I want you to find it. So, what would be the fastest solution? If I tell you higher or lower, from 1 to 100, what would be your first guess? Exactly, 50. Because what we want to do, and I will go to the whiteboard. By the way, no one actually did say the number, I should note. What I will do is I will take the space. Green doesn't work well. Where did my... There it is. This is the... Exactly. If you took 1110 or 1111, it's the Python player assignment. So we're going to take our search space from 1 to 100. And what we're going to do is you can think of this as we're going to divide in half. And I'm going to guess 50. And either the number is lower or it's greater. Now, in this case, the number that I wrote down is lower. So what I can do is I can say, well, if it's lower, it's not 50. It's also not any of these numbers. Now, exactly, the next guess would be 25. I divide my search space in half, 25. In this case, it's higher than 25. So I can throw away this part. Now notice, with only 2 guesses, I've reduced this search space to 26 to 49. It's now only 24 possible numbers. From here, 37.5. Well, it is a whole number, so we could round down. We could say 37, and it's higher than that. So I'm going to throw away this space. And eventually, by the way, the number is actually, hang on. Juliet, you just got it. Juliet L, you just got it. It was 47. See? There it is, 47. Anyway. The point here is this is what we call a divide and conquer strategy. And generally, divide and conquer, you get a 100 for course. That is not the statement of the professor. I'm just gonna go ahead and put that out there. This was not a giveaway or anything like that. The point is, this divide and conquer strategy is a log process, and here's why. I'll illustrate this again, going back to the whiteboard. If I were to say guess a number 1 to 10, I have 10 possible values. In a worst case, you can always win this game if I give you 4 guesses. If I double this number to 20, in a worst case, you can always win with 5 guesses. If I double this number to 40, in a worst case, you can always win with 6 guesses. This pattern continues. So if I gave you a number 1 to 1 million, 1 to 1 million, you would only need 20 guesses. And if I double this number to 2 million, you would only need 21. That is to say, doubling the size of this still only adds 1 guess. And so the rate of growth looks like this. It levels off. It's not, whereas linear maybe looks something like this, a straight line. This is a line that curves downward. Now it never starts decreasing. It approaches and doesn't even have an asymptote in this case. It always grows, but it grows more and more and more slowly. Gets a 47 for the course, exactly. Is there a general formula for this? Yes. The general formula is the number of guesses it takes from 1 to n is going to be the ceiling of log base 2 of n. That is to say, round this number up. So if it were like 7.1, you call that 8. I can't remember exactly what the ceiling looks like, but I think you would draw it that way. Also, so this is to say this formula is log base 2 of n. So this would be a divide and conquer strategy. Another way to think of this is searching a dictionary. You don't search a dictionary by reading from front to the back, right? You look in the middle, you determine if you need to look left or right. This would be called, a binary search, not a binary sort. But speaking of sorting, still not done. Anyway. So a binary search. We'll also talk about a binary search tree later in the class, and this is log. So now we get to linear. Linear, we've already given some examples, but a trivial example is traversing over an array that's linear. Double size of the array takes longer. Log linear is interesting. It tends to be sorting algorithms have a best case. No sorting algorithm can ever be better than n log n. There's actually a proof for this. But these are the best sorting algorithms. Worse than log linear is quadratic. If you make one, congratulations on your Turing Award, because you will win it. Because you will be flying in the face of all mathematics. So, best of luck. So quadratic time, as an example, would be a poor sorting algorithm, or you could do a pairwise comparison. That is, loop through an array and find every combination of every two values. That would be quadratic. Exponential time, we get even worse. An exponential time is really slow. We'll look at an example of this later. But an example is Towers of Hanoi. So Towers of Hanoi is a kids game of Hanoi. You can just... The number of steps this game takes to play, I'll play it with 3 discs real quick. The formula for the number of steps is actually quadratic. That is to say that if I have 4 discs, let's say 4 discs takes n steps. If I go to 5 discs, it takes 2n plus 1 steps. If I go to 6 discs, 2n plus 1 steps. Where n was the number for 5, etc. This is an exponential growth. And we'll do an example of this later. Exponential is really, really, really bad. So now, real quick, I need to pull up my downloads here. I'm going to pull up, where is it? This is a chart where what I did, and I will upload this, it's not uploaded yet, is I said, let's say that you have a computer that does 1 million operations per second. Technically, I didn't make this. This was a colleague back at Penn, Swap, but he's allowed me to use it. Swap Neil Sheth, if you want to look him up. This is to say, if n is size 10 and we have a constant time operation, it always takes one operation. Or for a constant time operation, one operation always takes 1 microsecond. That is 1/1,000,000th of a second. If we're looking at a log n function, size input 10 takes the same as constant time. But as this grows, you can see that every time I multiply the size of the input by 10, the runtime only increases by a microsecond. This barely grows at all. Linear time, you can see that every time I increase it exponentially, the runtime slows down exponentially, but this is still a good curve. You can do something with 1 million operations in 1 second for linear time, which makes sense. By the way, how is the sorting? That's a good question. It's not done yet. N log n, this process would take 6 seconds. N squared, this would take 11 days. N cubed, this would take 31,000 years. Substantially longer than all of written human history. N factorial with size 100 would take past the heat death of the universe as we currently estimate it. Same with exponential for size 1000. And by the way, there are algorithms that we believe can only be solved in polynomial time. So it is more tragic than it appears at first. So the point is, this really matters. And I hope this last demonstration convinces you that having efficient algorithms matter. What is an example of n factorial? A naive approach to traveling salesperson. So the idea is of traveling salesperson, I can just... By the way, you're going to do a homework on traveling salesperson, which it's not going to be as hard as maybe you're worried. Here I have 5 points. What path through these 5 points is the fastest that then has me return home at the end? Is it this one, or maybe it's this one? By the way, it's definitely not the purple one. The point is, the number of paths possible is n factorial. So a naive approach would be to look at every possible path and try to find the shortest, and that would be n factorial. Which is to say n factorial is bad. By the way, still not done. And in fact, I'm so convinced that this won't finish today that I'm just going to tell you it won't finish today, and you can trust me on that. This sort will not finish today. It will finish sometime around 2 to 3 a.m. based on my past experience. And I have a beefy computer. It can run Crysis. And this computer will still take until tomorrow 2 to 3 a.m. to finish. Well, just for the sake of demonstration... Just for the sake of demonstration, I'm going to instead, you remember how we talked about how there's this thing called a merge sort, and that merge sort is faster? Let's try this. Let's see how long this takes. So anyway, I start running the program, and it's done. It's done. The sorting is done. Let's try that again. Maybe that was a bad luck, and anyway, it's done. And it's done. What about bubble? Bubble is actually even worse than selection. Why even use the other sort? That's a great question. The answer is practically there's no reason. When we're dealing with large numbers. We do teach other sorts because they're useful tools to visualize how to move variables around, etc. But the point here is to say that you should you should use the most efficient sort, because that's the difference between this taking maybe 2 seconds versus taking over 12 hours. That's a huge difference, and it's only because of the algorithm I chose. These algorithms do the same thing. They sort information. But by picking the correct algorithm, and we'll talk about how these sorts work and why merge sort is faster on Monday, but picking the correct algorithm makes a massive, massive difference. And I'm now going to tell you a personal anecdote, and I know I'm almost up on time, so I apologize for being a minute over, but indulge me. In my grad program, what I had to do was I was writing a data mining program, and I needed to take a huge set of data, tens of thousands of lines, and I needed to remove all the lines that adhered to a rule and separate them into 2 lists. And the way I did it, and it's embarrassing as all hell, the way I did it was I managed to take that, which should have been linear, and I turned it into quadratic, because I used a find function, which is linear time inside of my loop. So linear inside of linear was quadratic. This ended up meaning that my program that I was trying to show off for my master's dissertation took literally hours to run on large data. And when I finally fixed this, because my professor insulted me enough, and he said, no, you're doing this wrong, and made fun of me, and I'm the kind of person that I'm like, I wanted to make him eat the words, and I fixed it. It was taking, for the largest data I had, 2 seconds, as opposed to hours. So the point is, picking the right algorithm really, 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 really matters. With that, there is an in-class activity today. I will go ahead and pull that up real quick. F, but in-class activities are opportunities to learn. That shouldn't be an F. That should be a yay. That should be PogChamp. Opportunity to learn. Is there a quiz this weekend? Yes, there is. Okay, that one admittedly might be an F. Will the results be the same regardless of the algorithm chosen? No. Will the results be the same? That is the sorted list. Yes, it will be. Sorry. The 2 algorithms are the way to get from problem to solution, but one of them is more efficient. Sorry. So go ahead and take a look. Sorry, there's about a billion questions that are showing up right now, so I will take a second. Sorry, I'm on the wrong class. I have 2 classes. You're not doing Tic-Tac-Toe GUI. Don't worry, that's my other class. And by the way, it's not as simple as Tic-Tac-Toe. It's actually a bizarre form of Tic-Tac-Toe. Anyway, you have the in-class activity today for algorithms. So you're going to download employee Java, employee catalog, and you're going to basically just follow these steps here. It's on CodeLab. Can we use a derivative of these functions to find its efficiency as n approaches infinity? I'm finding so when we're talking about big O notation, we are talking about n approaching infinity. The derivative of the calculus derivative would give you the rate of growth, sure, but the rate of growth would then need to be translated back to the actual runtime, which would involve integrating. So you'd be taking the derivative just to integrate again later. It's not that. Anyway. Are there limiting factors for runtime growth, i.e. exponential growth? I'm not sure what you mean by limiting factors. I certainly want the algorithm to finish before I die. So I'd probably want to avoid exponential for that reason, because I would like to see the end result of my work and before I die. I'm not sure what you mean by that. Certainly we want our code to run reasonably efficient. Anyway, with that, bad jokes are now allowed. What this means is put the answers in the text box. Just put the answers in the text box. We don't need the Java file. We just need the answers. So there was a joke, and it was what was it? Something about Frodo with 8 bits was a hobbit. I can't remember it. It was pretty lame, but I enjoyed it. By the way, classes is over here. I'll just so people don't have to stick around for this. Give me 1 second. 1 second. Okay. Class is now over. All right, bad jokes. Hit me with them. I want to become a programmer to fix printers and vacuums for the rest of my life. I'm gonna have to. Yeah. Okay, that makes sense. Oh, can we listen to sorting algorithms on YouTube? Yeah. So YouTube sorting algorithm animation. Actually, there's even a better one which I'll show you on Monday, which uses traditional European folk dance to teach sorting algorithms. I'm not going to show that one today because that is my surprise for you for Monday. Hang on, I have to route 1 second. I have to route the sound through my headset. Here we go. Why do programmers get Christmas and Halloween mixed up? Go ahead. Oh, sorry. No sound? You can't hear the... Huh. Hang on. Ah, yes, that's why. There you go. Because, yeah, that's good. There you go. That was a selection sort. This is an insertion sort. And I'll go ahead and link this video so you can watch it. You can see that the insertion sort, what it's actually doing is it's inserting the values in order as you go, but that means that the longer or the larger your sorted section gets, the longer each next step takes. This is a quick sort, which we actually won't talk about because it's a probabilistic algorithm, which is a bit weird. Also, the noises are fun. What concert costs just 45 cents? Anyway. Alright. What's the time complexity of a random sort? I don't know what you mean by a random sort. If you mean randomize the order and hope that it's sorted, technically that's a probabilistic algorithm, and that would be n factorial. 50 Cent and Nickelback, yeah. That would be a terrible concert because Nickelback. Yeah, you try going to high school when Nickelback was popular. It was really fucking terrible to listen to the radio. Pardon my language. Sorry. Sorry. My bad. Alright, anyway. BOGO sort. Oh, scroll for my joke, you missed it. Oh yeah, how do object-oriented programming kids become a wealthy inheritance? That's actually pretty good, not gonna lie. Would you rather eat 100 bricks? Ah, yes. What's the matter, baby? Yuck, 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 yuck. Yeah, I know that joke. Nothing, baby. What's the matter with you? Anyway, that did get deleted, and I'm not actually sure why, but anyway. All right, sorry. There was a joke that got deleted. It was, would you rather eat 100 Bix or a Matter Baby? And I'm supposed to say, what's a Matter Baby? And then he says, nothing. What's the matter with you? Tis the joke. Not gonna get caught on that one. And I know I've been caught before. Anyway, all right, I'm gonna wrap up the lecture because it is actually one, and this has nothing to do with class at this point. So I do actually have a ton of work to get one. Um, I like that one on I like that one on I'm subbed. For those on YouTube, it's I like telling dad jokes. Sometimes he laughs. Yeah. Anyway, take care, everyone. Have a good weekend. I'll see you all Monday. And this actually is the ending screen this time.